Lightning never strikes the same place twice, unless someone's controlling the weather. In 8 years, 3 impossible visitors have graced our solar system: mysterious Oumuamua, textbook Borisov, and now the enigmatic 3I-ATLAS with its alien chemistry. These cosmic ambassadors arrive just as our technology matures enough to study them properly. That's either the luckiest timing in human history or evidence of patience spanning geological ages. But what if 3I-ATLAS isn't just visiting? What if it was built for this moment? Its chemistry seems engineered for survival, its path calculated for discretion. In light of the most recent discoveries, the question might not be whether aliens exist, but whether they've learned to masquerade as comets. Settle in as we decode whether 3I-ATLAS was designed by physics or by something far more intentional. Part 1. The question we shouldn't ask. On July 1st, 2025, a robotic telescope in Hawaii captured something that shouldn't exist. Not a star, not a planet. Something moving through our solar system at 61 kilometers per second, fast enough to escape the sun's gravitational embrace entirely. This is 3I-ATLAS, the third confirmed interstellar object ever discovered. The I stands for interstellar, marking it as a visitor from beyond our cosmic neighborhood. But here's what makes your skin crawl. What if it wasn't just visiting? What if it was sent? Now, before you roll your eyes and dismiss this as science fiction, consider this. We're not asking whether little green men are piloting a spaceship through our solar system. We're engaging in something far more sophisticated, a disciplined thought experiment about intent behind an interstellar visitor. When we say designed, we're casting a wide net. This could be a probe, engineered to gather data about our solar system. It could be a beacon, broadcasting information across the cosmos. Perhaps it's a seed, carrying the building blocks of life between star systems. Or maybe it's simply a relic, ancient technology from a civilization that vanished eons ago, still drifting through space like a message in a bottle. Let's establish what we know, factually, about 3I-ATLAS. It was discovered by the Asteroid Terrestrial Impact Last Alert System, ATLAS for short, a network of telescopes designed to spot objects that might threaten Earth. The 3I designation tells us it's the third interstellar object we've confirmed, following 1I, Oumuamua, in 2017 and 2I, Borisov, in 2019. What makes it undeniably interstellar? Mathematics doesn't lie. This object follows a strongly hyperbolic orbit with an eccentricity of approximately 6.08. In celestial mechanics, anything above 1.0 means it's not bound to our Sunday. It's just passing through. Its velocity, at infinity, the speed it would maintain if the sun's gravity suddenly vanished, clocks in at 57 to 61 kilometers per second. For comparison, comets born in our solar system rarely exceed 42 kilometers per second, even when falling from the distant Oort cloud. Where is this cosmic wanderer headed? On October 30th, 2025, it will reach perihelion, its closest approach to the Sun, at approximately 1.4 astronomical units. That's just inside Mars's orbit. Earth will be safe, thankfully, as 3I-ATLAS will pass no closer than 1.6 to 1.8 astronomical units from our planet. No impact risk, but close enough for our most powerful telescopes to study it in unprecedented detail. Here's where things get interesting. Current size constraints place 3I-ATLAS at an upper limit of 5.6 kilometers across, though it could be as small as 320 meters. The Hubble Space Telescope captured it on July 21, 2025, revealing something remarkable: a visible coma, that fuzzy envelope of gas and dust, and a sun-warmed dust plume. This is comet behavior, exactly what we'd expect from a chunk of ancient ice and rock encountering solar radiation. But the chemistry tells a different story. On August 25, 2025, the James Webb Space Telescope trained its infrared eyes on 3I-ATLAS and found something unusual. The coma is dominated by carbon dioxide, CO2, with a ratio to water of approximately 8:1. Most comets in our solar system show the opposite. Water dominates, with carbon dioxide playing a supporting role. Even more intriguing, this CO2 enhancement appears stronger on the sunward side, as if responding to solar heating in ways that hint at formation near a CO2 ice line in some distant stellar system. Our observation window is precious and limited. Ground-based telescopes can track 3I-ATLAS clearly through September 2025, after which it disappears into solar glare. It won't re-emerge for follow-up observations until December 2025, giving us narrow windows to solve its mysteries. Now, let's clarify the rules of engagement for this investigation. We're not here to proclaim truth from shadows. We're exploring engineered object hypotheses alongside the standard comet model, maintaining strict separation between data and inference, between inference and imagination. We'll triangulate from the known anomalies of Oumuamua, the unusual chemistry of Borisov, and now the geometry and volatiles of 3I-ATLAS. Then we'll layer in established technosignature frameworks, the scientific methods researchers like Abraham Loeb and James Benford have developed to distinguish artificial objects from natural ones. Uncertainty is our constant companion here. We're still months away from perihelion as of this recording, so some of our claims remain provisional. We'll mark speculation plainly and cite only vetted facts, updating our understanding as new peer-reviewed results emerge. But here's the crucial point. Even asking this question, what if it was designed, pushes us to examine 3I-ATLAS with fresh eyes. It forces us to consider what signatures of intelligence might look like when disguised as natural phenomena. It challenges us to think like forensic scientists, not just astronomers. What if, just what if, we're not alone? And what if the evidence has been sailing past us at 61 kilometers per second, wearing the perfect disguise of a dirty snowball from the stars? The universe, it seems, still has secrets to whisper. The question is, are we listening carefully enough to hear them? Part 2. A Universe of Architects. Before we can recognize artificial design, we must first appreciate nature's own architectural mastery. The universe itself is the ultimate designer, forging complexity from chaos across billions of years. Stars design heavy elements through nuclear fusion, fusing hydrogen into helium, then carbon, oxygen, silicon, and iron in their cores. When these stellar furnaces exhaust their fuel and explode as supernovae, they scatter their creations across space, calcium for bones, iron for blood, oxygen for breath. We are, quite literally, made of star stuff. Gravity becomes the cosmic sculptor, shaping galaxies through mergers and cannibalism. Dark matter provides the invisible scaffolding upon which ordinary matter congregates, forming the cosmic web, vast filaments of gas and stars, separated by seemingly empty voids. What appears chaotic from our limited perspective reveals elegant structure when viewed across cosmic scales. Galaxy clusters flow along these filaments like beads on invisible strings, following patterns established by physics, not conscious intent. This process continues on smaller scales. Planetary systems emerge from swirling disks of dust and gas around young stars. Rocky planets condense closer to their parent stars, while gas giants form in the outer reaches where water and other compounds freeze into solid grains. Even life itself may be nature's masterpiece of engineering, self-replicating chemical systems that emerge from organic soup, evolving increasing complexity through natural selection. The point here isn't to diminish the wonder of natural processes, but to recognize their sophistication. If blind physical forces can yield such intricate structures, from the double helix of DNA to the spiral arms of galaxies, then intelligence might learn to imitate these same processes. An advanced civilization could build devices that exploit the same physics nature uses, creating artifacts that appear completely natural to casual observation. Consider biomimicry, which human engineers already employ extensively. Velcro mimics the hooks on burr seeds. Sonar technology borrows from echolocation in bats and dolphins. Aircraft wing designs copy bird feathers and insect wings. Japanese bullet trains adopted the streamlined beak shape of kingfisher birds to reduce air resistance. If we can copy nature's designs with our primitive technology, imagine what civilizations millions of years older might accomplish. They could build spacecraft that harness radiation pressure, like solar sails, but disguise this propulsion as natural outgassing. They could design probes that use gravitational slingshot maneuvers around planets and stars, making their trajectories appear like the chaotic orbits of rogue asteroids. Most cleverly, they could construct vehicles that look like comets, complete with ice shells that sublime in stellar heat, creating natural-looking tails while concealing sophisticated instruments within. Comets make particularly attractive camouflage platforms. They're abundant throughout the galaxy, with trillions estimated in our Oort cloud alone. They're self-cooling through sublimation, providing natural thermal management for delicate electronics. They're rich in volatiles like water, carbon dioxide, and carbon monoxide, compounds that could serve double duty as both propellant and concealment. The dust and gas in cometary comas can effectively hide thermal signatures from infrared telescopes while scattering light in ways that obscure surface details. This leads us into fascinating territory for technosignature research. Perhaps advanced civilizations have moved beyond the crude metal rockets and radio broadcasts that characterize our current technology. Instead of fighting natural forces, they've learned to work with them. Their artifacts might exploit ambient physics so skillfully that they become indistinguishable from astronomical phenomena. We can imagine several categories of such objects. Inscribed matter probes could carry information encoded directly into their atomic structure, messages written in isotope ratios or crystalline patterns that would survive for millions of years. Lurker probes might position themselves in gravitationally stable locations like Lagrange points, observing planetary systems for extended periods while appearing to be just another asteroid. Stealth reconnaissance vehicles could mimic comets, using their natural comas to hide sophisticated sensor arrays. The hypothesis space is vast, ranging from simple mechanical devices to exotic technologies we can barely conceptualize. But we must maintain high evidentiary standards. We're not looking for faces on Mars or pyramid alignments. We need reproducible, quantifiable signatures that deviate from well-understood natural processes in statistically significant ways. This brings us to 3I-ATLAS as a case study. Where does its chemistry, speed, and geometry fit within the catalogue of natural phenomena? And more importantly, where might it stand out? Its carbon dioxide-rich composition is unusual but not unprecedented among comets. Its hyperbolic trajectory clearly marks it as interstellar, but so do the orbits of natural debris ejected from other stellar systems. The beauty of this approach lies in its testability. If 3I-ATLAS is simply a natural comet from another star system, its behavior should conform to physical models developed from studying thousands of comets in our own solar system. Any significant deviations would demand explanation, either through new natural processes or, potentially, through artificial origins. Nature has already shown us that the universe is far stranger and more beautiful than our imaginations could have conceived. From quantum mechanics to general relativity, from extremophile bacteria to dark matter, reality consistently exceeds our expectations. Perhaps the greatest compliment we could pay to hypothetical alien engineers is to assume they've learned to work with these same natural forces that have shaped the cosmos for nearly 14 billion years. The universe is already full of architects. The question is whether some of them happen to be conscious. Part 3. Anatomy of an artifact. Reading 3I-ATLAS like an engineer. Let's dissect 3I-ATLAS like forensic scientists examining evidence. Every measurement tells a story. Every observation provides clues. If this object were engineered rather than natural, those clues should be detectable, subtle patterns that deviate from the chaos of cosmic debris. Start with geometry. 3I-ATLAS follows a nearly retrograde orbit, inclined at approximately 156 degrees to the plane of our solar system. This extreme inclination, combined with its hyperbolic eccentricity of 6.08, leaves no doubt about its interstellar origin. Natural objects can certainly acquire such trajectories through gravitational interactions in their birth systems or encounters during interstellar wandering. The velocity at infinity of 57 to 61 kilometers per second fits comfortably within the range expected for objects ejected from other stellar systems. But here's where an engineer's perspective becomes interesting. That trajectory brings 3I-ATLAS close enough to our Sun for detailed observation without approaching Earth. If this were a reconnaissance mission, it represents either poor targeting or excellent stealth, close enough to gather data about our solar system's magnetic field and solar wind environment, far enough to avoid triggering planetary defense responses. The brightness profile tells another layer of the story. Early imaging revealed a compact coma with a sun-warmed dust plume extending in the anti-solar direction, exactly what we'd expect from a comet encountering increasing solar radiation. Hubble Space Telescope observations on July 21st captured what appears to be the beginning of a tail formation. So far, nothing unusual for a comet at 3.3 astronomical units from the Sunday. Size constraints place the nucleus at less than 5.6 kilometers in diameter, possibly as small as a few hundred meters. The nucleus itself remains unresolved even in our best telescopes, hidden within its growing coma of gas and dust. For comparison, Halley's Comet measures about 15 kilometers across, while the famous Hale-Bopp stretched nearly 60 kilometers. 3I-ATLAS sits at the smaller end of the comet spectrum, though still substantial enough to maintain activity across multiple orbits if it were bound to our Sunday. The chemistry reveals the most intriguing details. James Webb Space Telescope observations show a carbon dioxide-dominated coma with a CO2 to water ratio of approximately 8:1. This is genuinely unusual. Most comets in our solar system show the reverse pattern, with water ice dominating and carbon dioxide playing a minor role. Even more curious, this CO2's enhancement appears strongest on the sunward side, suggesting preferential heating or exposure patterns. Natural analogues do exist. Comet 2Y, Borisov showed unusually high carbon monoxide concentrations, hinting at formation in extremely cold regions of its parent stellar system. Some comets in our own system, like C 2016 R2, Pan-STARRS, have shown CO and CO2 dominance over water, but ratios matter. The specific composition of 3I-ATLAS could tell us about temperature gradients and chemical processes in its birth environment. Now, let's apply an engineer's lens, purely speculatively. Could this staged shedding of dust and gas mimic natural fragmentation while concealing artificial processes? Imagine a probe designed to look like a comet, with an outer shell of ice and dust surrounding sophisticated instruments. As solar heating increases, the shell would sublime naturally, creating the expected coma and tail while potentially exposing or activating internal systems. What kind of data might such a disguised probe collect during its perihelion passage? Solar wind composition and magnetic field strength, cosmic ray flux and interplanetary dust density, the gravitational influence of planetary masses. Essentially, a comprehensive survey of our solar system's physical environment, information valuable for any civilization considering future visits or colonization efforts. But here's the crucial reality check. As of our current observations, no confirmed fragmentation events have occurred with 3I-ATLAS. Reports focus on normal comet behavior, coma development, tail formation, and volatile outgassing driven by solar heating. The object's trajectory shows no evidence of course corrections or artificial maneuvering. Its distance from Earth, never closer than 1.6 astronomical units, argues against any Earth-targeted reconnaissance mission. This presents an important test for the artifact hypothesis. If 3I-ATLAS were designed for Earth observation, its trajectory planning seems remarkably poor. Unless, of course, the goal wasn't Earth observation but rather heliospheric sampling, measuring conditions throughout our solar system rather than focusing on any particular planet. What observations could falsify artificial origin claims? Detection of typical dust and ice grain size distributions matching natural comet norms would support natural origin. Isotope ratios consistent with stellar nucleosynthesis models would be another strong indicator. Spectroscopic lines showing only known ices and minerals, with no unusual molecular signatures, would point toward natural processes. Conversely, certain discoveries could strengthen the artifact hypothesis. Detection of refined metals or artificial compounds in the coma would be smoking gun evidence. Modulated or pulsed emissions uncorrelated with solar forcing might indicate internal power sources or communication systems. Anomalous thermal signatures suggesting internal heat generation could hint at artificial systems. The approaching perihelion passage offers our best opportunity to gather decisive data. As 3I-ATLAS reaches its closest approach to the Sun around October 30th, 2025, solar heating will intensify dramatically. High-resolution spectroscopy from the James Webb Space Telescope, Keck Observatory, and the Very Large Telescope could reveal the detailed composition of sublimating materials. Any artificial compounds or unusual isotope ratios should become detectable at this time. Time-variable monitoring could reveal patterns in dust and gas production that don't correlate with solar heating curves. Natural comets show relatively smooth increases in activity as they approach perihelion, driven primarily by increasing temperature and sublimation rates. Artificial objects might display different patterns, periodic bursts, asymmetric jets, or activity that doesn't track solar forcing. For now, 3I-ATLAS remains a fascinating natural phenomenon masquerading as something potentially more. Every measurement pushes us closer to understanding its true nature. Like archaeologists carefully brushing dirt from ancient artifacts, we're excavating the secrets of an interstellar visitor, one spectrum at a time. The beauty lies not in confirming our wildest speculations, but in the precision of the scientific method itself, our ability to distinguish between what we hope to find and what nature actually reveals. Part 4. Echoes of Oumuamua, the First Knock. To understand why 3I-ATLAS matters, we must first revisit the cosmic mystery that started it all. On October 19, 2017, astronomers discovered something unprecedented. 1I, Oumuamua, the first confirmed interstellar visitor to our solar system. What began as routine asteroid observations quickly evolved into one of the most contentious scientific debates of the 21st century. Oumuamua, meaning scout in Hawaiian, displayed behavior that challenged our understanding of natural objects. As it rounded the Sun and began its exit from our solar system, careful tracking revealed a non-gravitational acceleration. This wasn't unusual by itself. Comets routinely experience such accelerations when jets of sublimating gas create thrust, like tiny rocket engines. But here's what made scientists uncomfortable. No visible outgassing accompanied this acceleration. The Spitzer Space Telescope, optimized for infrared observations that should easily detect the warm dust typically associated with comet activity, saw nothing. No carbon dioxide, no carbon monoxide, no water vapor, none of the usual suspects that drive comet jets, yet something was pushing Oumuamua faster than gravity alone could account for. This anomaly spawned a cottage industry of exotic explanations. The hydrogen iceberg model proposed that Oumuamua was composed primarily of molecular hydrogen ice, which would sublime invisibly as it approached the sundae. The nitrogen iceberg hypothesis suggested it was a fragment of Pluto-like crust, rich in frozen nitrogen, that would also sublime without visible signatures. Other models proposed it was a loose aggregate of dust and pebbles, held together weakly enough that internal gas pressure could cause acceleration without obvious plumes. Each model faced challenges. Hydrogen icebergs shouldn't survive the radiation environment of interstellar space for millions of years. Nitrogen icebergs would require implausibly large parent bodies like Pluto. Dust aggregates should produce detectable thermal emissions that Spitzer didn't observe. Enter Abraham Loeb and Shmuel Bialy with their 2018 paper proposing that Oumuamua's acceleration could be explained by radiation pressure acting on an extremely thin, lightweight object, essentially a natural light sail or debris from an artificial one. This hypothesis proved beautifully testable. Objects with the right mass to area ratio would experience exactly the observed acceleration purely from solar radiation pressure. No mysterious invisible gases required. The scientific community's response was swift and largely critical. Extraordinary claims require extraordinary evidence, and the radiation pressure hypothesis made several assumptions that seemed improbable for natural objects. How would nature create such thin, rigid structures? How would they survive interstellar travel without fragmenting? Why was Oumuamua tumbling in such an unusual pattern if it were sheet-like? But here's why Oumuamua matters for our investigation of 3I-ATLAS. It expanded the acceptable anomaly space. Before 2017, interstellar visitors existed only in theory. Now we know they're real, they're detectable, and they can display unexpected behavior that challenges our models of natural processes. We must be careful about pattern seeking, though. 2 data points don't establish a trend, especially when those points are so different. Oumuamua showed no detectable volatiles and unusual acceleration. 2Y, Borisov, discovered in 2019, behaved like a textbook comet with abundant carbon monoxide and normal outgassing. Now 3I-ATLAS presents yet another variation, carbon dioxide-rich chemistry that's uncommon but not unprecedented among comets. This diversity actually argues against a single design pattern for interstellar artifacts. If aliens were sending probes to our solar system, we might expect some consistency in their design philosophy. Instead, we're seeing variety that suggests natural origins from different stellar systems with varying formation conditions. The comparison becomes more interesting when we consider observational selection effects. Our current survey systems, Pan-STARRS, ATLAS, Catalina Sky Survey, Linear, can only detect relatively bright objects. We're sampling the tip of an enormous iceberg, seeing only the largest or most reflective interstellar debris. The Vera Rubin Observatory, coming online soon, will increase detection rates dramatically and reveal whether the apparent diversity of interstellar objects continues or whether patterns emerge with larger sample sizes. What would genuine designed echoes look like across multiple objects? Shared non-random traits that couldn't arise from natural formation processes, similar unusual volatile mixtures, comparable spin states or thermal properties, trajectories that cluster around particular regions of the sky or show evidence, of course, corrections. Current laboratory tests of 3I-ATLAS spectroscopy show no such patterns. Its carbon dioxide dominance differs markedly from Borisov's carbon monoxide richness and Oumuamua's apparent lack of volatiles. If anything, this chemical diversity supports the hypothesis that we're observing natural debris from multiple stellar systems with different formation environments. Yet we shouldn't dismiss the artifact hypothesis entirely. Advanced engineering might deliberately create diversity to avoid detection patterns. Or we might be seeing different classes of objects, some natural, some artificial, mixed together in ways that current observations can't distinguish. Think of it as a psychological test writ large. If the universe were trying to get our attention, repeated unusual visitors might represent stimuli designed to provoke response. 3 anomalous objects in 8 years could be coincidence, or it could be the opening notes of a longer message. The Vera Rubin Observatory will help answer this question by dramatically increasing our detection rate of interstellar objects over the next decade. For now, 3I-ATLAS represents our best opportunity yet to spectroscopically characterize an interstellar visitor before it reaches perihelion. Unlike Oumuamua, which was discovered only after its closest solar approach, we have months to plan detailed observations of 3I-ATLAS as solar heating drives increasingly vigorous activity. The James Webb Space Telescope observations from August 25th represent just the beginning of this investigation. As 3I-ATLAS approaches perihelion, we'll watch its behavior with unprecedented precision, searching for patterns that distinguish artificial from natural processes. Oumuamua gave us the first knock on the door of possibility. 2I, Borisov showed us what normal interstellar comets look like. Now 3I-ATLAS provides our third data point in this cosmic game of pattern recognition. Whether that pattern ultimately reveals natural diversity or something more profound remains to be determined by careful observation and rigorous analysis. The universe, it seems, is teaching us patience and the value of keeping our minds open while maintaining the highest standards of evidence. Part 5. The Dark Forest Parallel. Liu Cixin's science fiction trilogy, The Three-Body Problem, introduced millions of readers to a chilling concept, the dark forest hypothesis. In this framework, the universe resembles a dark forest where every civilization is a hunter, moving stealthily through the trees, because making noise, broadcasting your location, invites destruction from other hunters. Survival depends on silence. But what if survival also requires information? This fictional framework, while purely speculative, offers a useful lens for examining interstellar reconnaissance strategies. If civilizations exist throughout the galaxy but maintain radio silence for defensive reasons, how might they gather intelligence about potentially habitable star systems? Small deniable artifacts could sample environments without revealing the sender's location or capabilities. Let's apply this logic to 3I-ATLAS. Its trajectory brings it through our solar system without approaching Earth closely, never nearer than 1.6 astronomical units. If this were a reconnaissance mission, it seems poorly designed for Earth-specific surveillance. But perhaps Earth was never the primary target. Consider what valuable information a disguised probe could gather during a solar system flyby. Solar wind composition and magnetic field strength would reveal the star's age and activity level. Planetary masses and orbits could be measured through gravitational perturbations. The presence and distribution of dust and debris throughout the system would indicate asteroid belt characteristics and comet populations. Most importantly, the probe could sample the heliospheric boundary conditions that would affect future interstellar missions to this system. This kind of reconnaissance makes strategic sense across million-year timescales. Galactic civilizations, if they exist, might operate with patience that dwarfs human historical experience. A single probe passing through a star system could gather baseline data for future reference, even if no immediate follow-up missions are planned. The investment is minimal, one small, expendable object, while the information gathered could prove valuable centuries or millennia later. The beauty of this approach lies in its deniability. Objects like 3I-ATLAS could be dismissed as natural debris unless detailed analysis revealed clearly artificial signatures. Even then, the probe's origin would remain uncertain. Was it sent by a civilization in Vega, Proxima Centauri? Some unnamed star system hundreds of light-years away? The sender's identity and location would remain protected. Compare this to the Lurker hypothesis proposed by researchers like James Benford. Lurker probes would position themselves in gravitationally stable locations, Lagrange points, co-orbital positions with planets, or long-period asteroid-like orbits, where they could observe target systems for extended periods. These represent a different strategic approach, permanent monitoring stations versus temporary reconnaissance flybys. 3I-ATLAS doesn't fit the Lurker profile. Its hyperbolic trajectory will carry it out of our solar system permanently, never to return. This suggests either a one-time sampling mission or simply a natural object following the gravitational dynamics that govern all interstellar debris. But let's consider the risk calculus from an alien perspective. If hostile civilizations really do exist, artifacts designed for maximum ambiguity might be the safest approach to intelligence gathering. A probe that looks exactly like a comet, behaves exactly like a comet, and reveals no artificial signatures to casual observation would be virtually undetectable to primitive civilizations like ours. The irony is that 3I-ATLAS's very visibility works against the stealth hypothesis. Its bright coma and tail make it easily detectable to ground-based telescopes, drawing exactly the kind of attention that a covert mission would want to avoid. Unless, of course, that visibility is part of the camouflage. What better disguise for sophisticated instruments than the natural fireworks display of a sublimating comet? If you wanted to be seen, if the goal were announcement rather than stealth, the trajectory still seems suboptimal. A closer Earth approach would have guaranteed more attention from human observers and allowed more detailed study of our planet's characteristics. Instead, 3I-ATLAS passes by at a respectful distance, gathering data about our solar system's general properties while avoiding any appearance of Earth-specific interest. This analysis reveals a fundamental challenge in technosignature research, distinguishing between poor design and deliberate ambiguity. An obviously artificial object would be easy to identify, but might represent a diplomatic or scientific contact attempt rather than covert surveillance. A perfectly camouflaged probe would be undetectable by definition. We're looking for objects that fall somewhere between these extremes, artificial enough to be recognizable with careful analysis, but natural enough to maintain plausible deniability. Current observations of 3I-ATLAS don't support the reconnaissance hypothesis strongly. Its carbon dioxide-rich chemistry, while unusual, falls within the range of natural variation observed among comets. Its coma and tail development follow predictable patterns based on solar heating and volatile sublimation. No obviously artificial signatures have been detected in its spectrum or morphology. Yet the dark forest framework reminds us to consider motivations and methods that might be completely alien to human experience. We assume that reconnaissance would target Earth specifically, but perhaps the goal is characterizing stellar environments more generally. We expect artificial objects to reveal themselves through technological signatures, but perhaps advanced engineering has learned to work entirely within natural physical processes. The question of response becomes ethically complex if we ever do identify genuinely artificial interstellar visitors. Do we attempt communication? Do we observe quietly while maintaining our own defensive silence? Do we ignore such objects entirely to avoid alerting potentially hostile observers to our capabilities? For now, these remain philosophical thought experiments rather than practical concerns. But they sharpen our observational criteria and remind us that the absence of obvious artificial signatures doesn't necessarily prove natural origin. Sometimes the best hiding place is in plain sight, disguised as something so ordinary that no one looks twice. The universe may indeed be a dark forest. But even hunters sometimes leave tracks, and patient observers sometimes spot the shadows moving between the trees. Part 6. Seeds in the Galactic Wind. Imagine life itself as a cosmic wanderer, carried between star systems not by spacecraft but by comets and asteroids drifting through the interstellar medium. This concept, called panspermia, suggests that life could spread throughout the galaxy through natural processes, or perhaps with some deliberate assistance. The basic idea isn't new. In 1973, Nobel laureate Francis Crick and chemist Leslie Orgel proposed directed panspermia, the hypothesis that life on Earth might have originated from microorganisms deliberately sent by an extraterrestrial civilization. This wasn't science fiction speculation, but a serious scientific hypothesis, testable through biochemical and genetic analysis of Earth's biosphere. Crick and Orgel noted several puzzling features of terrestrial biology that might support an artificial origin. The genetic code appears nearly universal across all known life forms, suggesting a single origin point rather than multiple independent developments. Certain trace metals like molybdenum play crucial roles in terrestrial biochemistry despite being relatively rare in Earth's crust, while more abundant metals like chromium and nickel are largely unused by biological systems. This pattern might reflect the chemistry of a different world where these trace elements were more readily available. Modern research has revealed that natural panspermia, lithopanspermia, is not only possible but probably inevitable. Asteroid and comet impacts can blast rocks off planetary surfaces with enough velocity to escape gravitational attraction. Some of these rocks, now traveling through interstellar space, undoubtedly carry microorganisms in their crystal matrices, protected from radiation and cosmic ray exposure by meters of stone. Comets make particularly attractive vehicles for such biological cargo transport. Their icy compositions provide natural refrigeration, maintaining near absolute zero temperatures throughout most of their interstellar journeys. They're rich in organic compounds, carbon-based molecules that form the building blocks of terrestrial biochemistry. When they encounter stellar radiation, they sublime gently rather than experiencing the shock heating that might sterilize rocky debris. This brings us to 3I-ATLAS and its unusual chemistry. The James Webb Space Telescope detected a carbon dioxide-dominated coma with CO2 to water ratios of approximately 8:1. While this composition seems unusual compared to comets in our solar system, it might reflect formation conditions in a very different stellar environment, perhaps around a star with different luminosity, or in a protoplanetary disk with different temperature gradients. But here's where the speculation becomes tantalizing. What if this unusual chemistry isn't just revealing the formation environment, but actually represents a preservation medium for complex organic molecules? Carbon dioxide makes an excellent protective matrix for biological materials, maintaining stable low temperatures while providing chemical buffering against radiation damage. If you were designing a long-term preservation system for biological samples, you might choose exactly this kind of chemical environment. The library in ice concept extends this logic further. Instead of carrying living organisms, interstellar comets might transport information, genetic codes, biochemical instructions, or even digital data encoded in crystalline matrices. Such information could survive for millions of years in the cold vacuum of interstellar space, essentially creating a galactic backup system for biological and technological knowledge. This approach offers significant advantages over radio transmission. Electromagnetic signals decay with distance and can be disrupted by stellar interference. Physical media, properly protected, can carry vastly more information with perfect fidelity across arbitrarily long distances. A single comet-sized object could transport the equivalent of Earth's entire digital library while appearing completely natural to casual observation. Reality check time. No instrument has detected biological materials or anomalous organic compounds in 3I-ATLAS. The approaching perihelion observations from James Webb and ground-based telescopes could tighten these constraints significantly. As solar heating drives increasingly vigorous outgassing, any complex organic molecules should become detectable through spectroscopic analysis. Compare 3I-ATLAS to its predecessor, 2Y, Borisov, which showed abundant carbon monoxide that implied formation in extremely cold regions of its parent stellar system. This chemical signature supported natural formation scenarios while revealing the diversity of protoplanetary disk environments throughout the galaxy. 3I-ATLAS's carbon dioxide signature might tell a similar story about temperature gradients and chemical processes in some distant stellar nursery. The delivery problem presents another constraint on directed panspermia scenarios involving 3I-ATLAS. Its closest approach to Earth exceeds 1.6 astronomical units, far too distant for any kind of biological seeding mission. Even if it carried living organisms or genetic material, that cargo would continue past us into the outer solar system and eventually back to interstellar space. But perhaps precision targeting was never the goal. Instead of aimed delivery to specific worlds, the directed panspermia hypothesis might envision a galactic drift seeding strategy. Billions of seed-carrying comets launched over millions of years, scattered throughout the galaxy with no specific targets in mind. Statistical mechanics would ensure that some fraction eventually encounters suitable planetary systems, while the vast majority continues wandering through space indefinitely. This approach mirrors strategies already observed in terrestrial biology. Dandelion seeds don't target specific patches of soil, they're released in vast numbers to be carried by wind currents, with success measured in probabilistic terms rather than precision delivery. Spores from fungi and bacteria follow similar dispersal strategies, colonizing new environments through sheer numbers rather than selective targeting. What observational evidence could support biological cargo in 3I-ATLAS? Detection of prebiotic organic compounds, amino acids, nucleotides, lipids, with isotopic ratios that differ from solar system norms would be highly suggestive. Discovery of stereoisomer preferences, molecular handedness, matching terrestrial biology might indicate common origins. Most compelling would be detection of clearly biological polymers, proteins, DNA, RNA, that couldn't arise from purely chemical processes. Current spectroscopic capabilities make such detections extremely challenging, but not impossible. As 3I-ATLAS approaches perihelion and outgassing intensifies, the most sophisticated instruments on Earth will be watching for exactly these kinds of molecular signatures. The philosophical implications extend far beyond biology. If life can spread naturally between star systems, then the galaxy might be far more connected than we imagine. Rather than isolated islands of evolution, planetary biospheres could represent nodes in a vast network of genetic and biochemical exchange operating on million-year timescales. Whether that network emerged purely through natural processes or received some deliberate assistance remains an open question. But 3I-ATLAS, with its unusual chemistry and interstellar origin, represents our best current opportunity to search for answers. It carries with it the chemical fingerprints of another world, another time, and possibly, just possibly, another form of life entirely. Even if 3I-ATLAS proves to be nothing more than frozen gases and rocky debris from some distant stellar system, it still carries a message. It tells us about the chemistry of worlds we'll never visit, the physics of environments we'll never experience directly, and the processes that shaped matter in regions of space separated from us by light years and eons. In that sense, every interstellar visitor is already a library, a repository of information about cosmic processes and planetary formation. The question is whether some of those libraries were assembled by librarians. Part 7. Alien Engineering 101. Arthur C. Clarke's third law states that any sufficiently advanced technology is indistinguishable from magic. But there's a corollary that might be even more relevant to our investigation. Any sufficiently advanced technology might be indistinguishable from nature itself. If you wanted to build a probe that could travel between star systems undetected, you'd design it to exploit the same physical processes that govern natural objects. Let's approach this as an engineering exercise. What design requirements would constrain an interstellar reconnaissance probe? First, it must survive the journey, potentially millions of years in the harsh environment of interstellar space, bombarded by cosmic rays and micrometeorites. Second, it must harvest local energy upon arrival, since carrying fuel across such distances would be prohibitively expensive in terms of mass and volume. Third, it must blend seamlessly with natural debris to avoid detection by primitive civilizations. Fourth, it should possess some capacity for self-repair or adaptive response to changing conditions. The solution practically designs itself. Build your probe like a comet. Ice provides natural radiation shielding, protecting delicate electronics from cosmic ray damage during the interstellar crossing. Water, carbon dioxide, and carbon monoxide ices offer excellent thermal buffering, maintaining stable low temperatures that preserve both biological samples and electronic components. These same volatiles become fuel for maneuvering once the probe encounters stellar radiation. Sublimation creates natural jets that can provide thrust for course corrections while appearing completely normal to observers. The outer layers of dust and ice serve multiple functions. They scatter sunlight in ways that obscure surface details and thermal signatures. They provide raw materials for self-repair through controlled sublimation and redeposition. Most cleverly, they create the spectacular light show of coma and tail formation that draws attention away from the probe's core functions while appearing to be nothing more than natural comet activity. Propulsion becomes elegantly simple through biomimicry of celestial mechanics. Use gravity assists around planets and stars to adjust trajectory, a technique human engineers already employ routinely. Harness solar radiation pressure for fine course corrections, again mimicking natural processes that affect all small bodies in stellar systems. Time these maneuvers to coincide with natural outgassing events that would create similar accelerations in genuine comets. Instrumentation can be embedded within the ice matrix, protected from detection by meters of natural camouflage. Sensors for magnetic fields, particle density, gravitational variations, and electromagnetic radiation could operate continuously while appearing to casual observers as nothing more than irregular lumps in the comet's nucleus. Data storage could utilize the probe's own molecular structure, information encoded in isotope ratios, crystal orientations, or organic polymer sequences that would survive indefinitely in the cold vacuum of space. Communication presents interesting challenges and opportunities. Traditional radio transmission would risk detection and reveal artificial origin, but the probe could modulate its natural emissions, varying the composition or timing of outgassing in ways that encode information. Such signals would appear as natural variations in comet activity, unless observers knew exactly what patterns to look for. Failure modes become features rather than bugs in this design philosophy. As the protective ice shell erodes under stellar heating, internal systems become exposed, but this looks exactly like the normal evolution of comet nuclei approaching perihelion. Components might be designed to fragment in controlled ways that mimic natural breakup events, while dispersing multiple smaller probes throughout the target system. Power generation exploits temperature differentials between the sun-facing and shadowed sides of the probe, using thermoelectric effects that produce no detectable emissions. Energy storage could utilize phase transitions in the ice matrix itself, essentially turning the entire probe into a battery that charges and discharges through natural heating and cooling cycles. The engineering elegance of such a system lies in its complete integration with natural physics. Every artificial component serves multiple functions while maintaining perfect camouflage. The probe doesn't fight against natural forces, it harnesses them, becoming a technological Aikido master that redirects cosmic energy flows to serve its purposes. Now, let's apply this speculative framework to 3I-ATLAS. Its carbon dioxide-rich chemistry could represent a sophisticated preservation medium for instruments or biological samples. The sunward enhancement of CO2 emissions detected by James Webb might indicate selective heating of surfaces designed to activate at specific solar distances. The compact, unresolved nucleus could conceal sophisticated systems beneath layers of natural ice and dust. But here's the crucial discipline. Absence of evidence is not evidence of absence, but it's also not evidence of presence. 3I-ATLAS has shown no confirmed signatures that deviate from natural comet behavior. Its spectral emissions match known ice sublimation processes. Its trajectory follows gravitational dynamics with no apparent course corrections. Its morphology resembles thousands of comets observed in our own solar system. The burden of proof sits firmly with extraordinary claims. If 3I-ATLAS were an artificial probe, we should be able to detect some signature that distinguishes it from natural objects, modulated emissions, anomalous thermal patterns, unusual grain compositions, or isotopic ratios that don't match stellar nucleosynthesis models. Our observational wish list for the approaching perihelion passage includes high-resolution spectroscopy across multiple wavelengths, time-variable monitoring of dust and gas production, polarimetry to characterize grain properties, and thermal imaging to map surface temperature variations. These observations could potentially reveal artificial signatures while simultaneously advancing our understanding of interstellar comet physics. The comparison with 1I, Oumuamua, remains instructive. That object's non-gravitational acceleration without visible outgassing gave some plausibility to artificial surface hypotheses, perhaps a light sail-like structure exploiting radiation pressure. But the engineering interpretation remains contested, with multiple natural explanations still under consideration. This design exercise serves a valuable purpose regardless of 3I-ATLAS's true nature. It sharpens our observational criteria, suggests specific tests for distinguishing artificial from natural phenomena, and reminds us that advanced technology might be far subtler than our current assumptions suggest. Whether 3I-ATLAS represents advanced alien engineering or simply the fascinating natural physics of interstellar debris, it's teaching us to see the universe with fresh eyes. Sometimes the most profound discoveries emerge not from confirming our expectations, but from learning to ask better questions about the cosmic mysteries sailing past us at 61 kilometers per second. Part 8. Cosmic Camouflage and the Anti-Tail Illusion. Nature loves optical illusions, and nowhere is this more apparent than in the ethereal displays created by comets. Understanding these natural light shows becomes crucial when evaluating whether unusual morphology might indicate artificial origin or simply represent physics playing tricks on our perception. Let's start with basic comet anatomy. As these icy wanderers approach the Sun, solar radiation heats their surfaces, sublimating frozen volatiles into gas that forms the coma, that fuzzy envelope surrounding the nucleus. Solar wind, a stream of charged particles flowing outward from the Sun, pushes ionized gas directly away from our star, creating the ion tail that always points anti-solar regardless of the comet's motion. Meanwhile, radiation pressure acts on dust particles liberated by sublimating ice, forming the dust tail that curves along the comet's orbital path due to the particle's momentum. But sometimes, observers see something that seems to defy these rules: a sunward spike extending from the comet's head, appearing to point directly toward the Sun rather than away from it. This anti-tail looks so unnatural that early astronomers wondered if they were witnessing some kind of propulsion system. The explanation is pure geometry. Large dust grains, too massive to be significantly affected by radiation pressure, remain close to the comet's orbital plane. When Earth crosses this plane, we see these particles edge on, creating an optical illusion of material extending toward the Sunday. It's the same effect that makes Saturn's rings appear as a thin line when viewed from their edge, despite being thousands of kilometers thick. Historical examples abound. Comet Bradfield in 1975 displayed a spectacular anti-tail that persisted for weeks. Comet Kohoutek showed similar features in 1973 and 74. More recently, Comet ZTF displayed sunward spikes during its 2023 apparition, and Comet 3I-ATLAS A3 showed anti-tail features during its 2023 passage. This phenomenon matters for our investigation because it demonstrates how easily natural processes can create seemingly anomalous morphology. When evaluating claims about artificial objects, we must first exhaust natural explanations, even those that initially appear to violate physical intuition. 3I-ATLAS has already begun showing morphological evolution consistent with normal comet behavior. Hubble Space Telescope imaging revealed a teardrop-shaped coma with a sun-warmed dust plume extending in the anti-solar direction. Early hints of tail formation appeared exactly where comet physics predicts, driven by the increasing intensity of solar radiation as the object approaches perihelion. The James Webb Space Telescope observations add another layer of understanding. The sunward enhancement of carbon dioxide emissions correlates precisely with illumination patterns. The sun-facing hemisphere receives more energy and therefore shows more vigorous outgassing. This behavior tracks solar forcing rather than any internal activity cycle, supporting natural rather than artificial explanations. But let's consider what would genuinely surprise us. Periodic dust pulses, uncorrelated with solar distance, would demand explanation through either previously unknown natural processes or artificial control systems. Jet activity that maintained constant intensity regardless of solar heating would violate basic thermodynamics. Dust grains with unusual compositions or size distributions might indicate manufacturing rather than natural condensation processes. Even more subtle signatures could reveal artificial origin. Natural comet jets typically show turbulent, chaotic structure as they interact with solar wind and radiation pressure. Artificially controlled jets might display more regular patterns, quantized intensity levels, geometric spray angles, or timing synchronized to celestial mechanics in ways that natural processes wouldn't produce. Observational campaigns coordinated across multiple telescopes could potentially detect such anomalies. Simultaneous imaging at different wavelengths might reveal thermal signatures inconsistent with purely solar heating. Polarimetry could characterize dust grain properties, distinguishing between naturally condensed particles and potentially manufactured alternatives. Spectroscopy could search for molecular emissions that don't match standard ice sublimation models. The cautionary tale of Comet Ison remains relevant here. This object fragmented spectacularly as it approached the Sun in 2013, demonstrating that dramatic morphological changes near perihelion are not rare events requiring artificial explanation. Comets represent loosely bound aggregates of ice, dust, and rock that can respond unpredictably to thermal stress and tidal forces. Current observations suggest 3I-ATLAS remains intact as it approaches its October 30th perihelion passage. But if fragmentation does occur, we must resist the temptation to interpret such events as evidence of artificial origin unless they display patterns clearly inconsistent with natural breakup mechanisms. The broader point extends beyond comet morphology to all aspects of anomaly hunting in space. Human pattern recognition evolved to detect meaningful signals in noisy environments, rustling bushes that might conceal predators, faces in crowds that might indicate social allies or threats. But this same pattern recognition can generate false positives, seeing intention where only physics operates. Advanced image processing and statistical analysis help mitigate these cognitive biases. Machine learning algorithms can identify subtle patterns in spectroscopic data that human observers might miss while avoiding the pareidolia, seeing faces in clouds that affects visual interpretation. But ultimately, extraordinary claims require extraordinary evidence, and that evidence must be reproducible across multiple independent observations. 3I-ATLAS continues to look remarkably normal by comet standards, despite its interstellar origin and unusual chemistry. Its anti-tail, if one develops during the approaching plane-crossing geometry, will almost certainly prove to be the same optical illusion that has fooled observers for centuries. Its jets and dust production follow predictable patterns based on solar heating and volatile sublimation, yet this normalcy shouldn't disappoint us. Every observation adds to our understanding of interstellar objects and the diversity of conditions in distant stellar systems. Whether artificial or natural, 3I-ATLAS represents a messenger from another world, carrying information about cosmic processes we can study in no other way. The universe provides us with natural magic tricks spectacular enough to inspire wonder without requiring artificial intervention. Sometimes the most profound discoveries come from understanding how nature performs its illusions rather than from discovering that wizards actually exist. Part 9. Memory of Lost Civilizations. Imagine 3I-ATLAS not as a spy or messenger, but as something far more poignant, a relic. A cosmic artifact from a civilization that vanished eons ago, now wandering the galaxy like a message in a bottle cast into an ocean of stars. This possibility transforms our investigation from a search for active intelligence to an exercise in galactic archaeology. The mechanism for creating such relics is surprisingly mundane. Planetary formation is a chaotic process involving gravitational interactions between countless bodies over millions of years. During the late heavy bombardment period that characterized early stellar system evolution, massive gravitational perturbations can eject substantial debris into interstellar space. Some of this material might carry the technological artifacts of civilizations that flourished and died while their parent systems were still settling into stable configurations. Consider our own solar system's violent youth. Jupiter's migration through the inner solar system likely scattered countless asteroids and comets, flinging them into interstellar trajectories. If technological civilizations had existed on early Earth or Mars during this chaotic period, their artifacts might now be wandering between the stars, indistinguishable from natural debris to casual observation. The lesson from 2I, Borisov becomes relevant here. This clearly natural interstellar comet carried distinctive chemistry, unusually high carbon monoxide concentrations that revealed conditions in its birth environment. The CO richness suggested formation in extremely cold regions of its parent stellar system, perhaps near the CO ice line where temperatures drop below -200 degrees Celsius. This chemical fingerprint persisted across the millions of years and light years of interstellar wandering. If technological artifacts could survive similar journeys, they might carry equally distinctive signatures, not just of their formation environment, but of the civilizations that created them. Unusual isotope ratios might indicate nuclear processes unknown in nature. Complex organic polymers could preserve information in molecular form. Even the bulk composition of such objects might reveal industrial processes rather than natural condensation. 3I-ATLAS offers our first opportunity to test these possibilities with cutting-edge spectroscopic analysis. The James Webb Space Telescope's detection of carbon dioxide-dominated chemistry provides a baseline for comparison with natural processes. As solar heating intensifies during the approach to perihelion, increasingly sophisticated molecular analysis might reveal whether this chemistry reflects natural ice condensation or something more complex. The concept of survival across cosmic timescales shouldn't seem implausible. Biological molecules can remain stable for millions of years under the right preservation conditions. DNA has been recovered from fossils hundreds of thousands of years old. Amino acids persist in meteorites that formed billions of years ago. Technological materials designed for longevity could potentially maintain structural integrity across even longer periods when protected by meters of ice in the vacuum of interstellar space. Information storage becomes particularly intriguing in this context. Rather than fragile electronic media that might degrade over geological time, advanced civilizations might encode information directly into atomic and molecular structures. Crystal lattices could preserve digital data through precise arrangements of dopant atoms. Organic polymers might carry genetic or cultural information in sequences analogous to DNA. Even isotope ratios could be artificially manipulated to create detectable patterns that convey meaning. The time capsule analogy extends beyond mere information storage to include actual technological components. Imagine a civilization facing extinction, perhaps from stellar evolution, asteroid impact, or climate change, that deliberately launched preserved samples of their technology into interstellar space. Not as an attempt at communication, but as a hedge against total obliteration. Some fraction of these technological seeds might eventually be discovered by other civilizations, preserving knowledge that would otherwise be lost forever. Current observations of 3I-ATLAS provide limited support for this scenario. Its Earth-Miss distance exceeds 1.6 astronomical units, making any kind of deliberate message delivery to our species unlikely. The trajectory suggests either random gravitational dynamics or possibly a mission designed to sample heliospheric conditions rather than target any particular planet. But perhaps precision targeting was never intended. A civilization launching technological relics might employ the same statistical strategy used by biological seed dispersal, release vast numbers of objects with no specific destinations, relying on chance encounters over millions of years to ensure some fraction eventually reaches suitable discoverers. The philosophical resonance of this possibility extends far beyond astrobiology. Throughout human history, artifacts have outlasted their creators. We study ancient civilizations primarily through their technological remnants, pottery, tools, buildings, artwork. These objects speak across centuries and millennia, preserving information about cultures that left no written records. If technological civilizations arise and fall throughout the galaxy on timescales comparable to stellar evolution, then interstellar space might be littered with similar artifacts. Some fraction of the objects we classify as asteroids, comets, and interstellar debris might actually represent the archaeological remains of vanished civilizations. This scenario makes testable predictions. Genuine technological artifacts should display material properties that distinguish them from naturally formed objects. Their isotope ratios should deviate from stellar nucleosynthesis models. Their mineral compositions might include refined metals or synthetic compounds unknown in natural processes. Most importantly, they might contain information, patterns in their molecular structure that convey meaning rather than simply reflecting physical and chemical formation processes. As 3I-ATLAS approaches perihelion, increasingly detailed spectroscopic analysis will test these possibilities. High-resolution observations could potentially detect the molecular signatures that would distinguish between natural ice condensation and deliberate technological construction. The challenge lies in recognizing such signatures when we encounter them, since we have no prior examples of alien technology for comparison. Even if 3I-ATLAS proves to be entirely natural, frozen gases and rocky debris from some distant stellar system, it still represents a form of message from the past. Its chemistry preserves information about conditions in its birth environment billions of years ago. Its journey carries data about interstellar conditions and the dynamics of matter exchange between stellar systems. In that sense, every interstellar visitor already serves as a time capsule, delivering information about cosmic processes we can study in no other way. The question that drives our investigation is whether some of those capsules might contain messages that are more than merely chemical, carrying the preserved thoughts and technologies of minds that once contemplated the same stars we see today. Ultimately, we're all archaeologists now, studying the artifacts that drift between the stars and wondering which ones might speak not just of physics, but of intelligence, fleeting glimpses of consciousness that flickered briefly in the cosmic dark and then scattered their memories to the galactic wind. Part 10. The Surveillance Hypothesis. What if 3I-ATLAS isn't trying to make contact? What if it's simply watching, measuring, cataloguing a cosmic intelligence gathering operation disguised as a routine astronomical event? This surveillance hypothesis transforms our investigation from a search for greetings into an analysis of reconnaissance capabilities. Consider the strategic logic from an alien perspective. Direct contact with a primitive civilization carries enormous risks. Cultural contamination could disrupt natural social evolution. Technological gifts might destabilize existing power structures or trigger destructive conflicts. Even peaceful communication attempts could provoke fear, hostility, or cargo cult behaviors that complicate future interactions. But information gathering presents fewer ethical complications. A civilization could learn everything necessary about a target system, stellar characteristics, planetary compositions, technological development levels, even basic cultural patterns, without ever revealing its presence or interfering with natural evolutionary processes. 3I-ATLAS's trajectory offers intriguing possibilities for such reconnaissance. While it never approaches Earth closer than 1.6 astronomical units, this distance places it well within the heliosphere, the bubble of solar wind and magnetic fields that surrounds our solar system. From this position, a sophisticated probe could sample conditions that reveal fundamental characteristics of our stellar environment. Solar wind composition varies with stellar age, magnetic field strength, and internal fusion processes. By analyzing particle density, energy spectra, and isotope ratios in the solar wind, observers could determine our Sun's evolutionary status, remaining lifespan, and stability characteristics. This information would be crucial for any civilization considering long-term interaction with our solar system. The heliospheric magnetic field carries signatures of solar activity cycles, coronal mass ejections, and other phenomena that affect planetary atmospheres and technological infrastructure. Understanding these patterns would be essential for timing future missions or communication attempts to avoid periods of high radiation or magnetic interference. Gravitational measurements could reveal the masses and orbital characteristics of planets throughout our solar system without requiring close approaches to individual worlds. Small perturbations in a probe's trajectory would indicate the presence and approximate size of planetary bodies, providing a census of potentially habitable environments. Even the cosmic ray environment within our solar system carries valuable intelligence. The heliosphere partially shields us from galactic cosmic rays, creating a unique radiation environment that affects both biological evolution and technological development. Characterizing this shielding would help external observers understand the conditions that shaped life on Earth and continue to influence our technological capabilities. From this perspective, 3I-ATLAS's Earth miss distance becomes a feature rather than a bug. Close planetary approaches risk detection and might trigger defensive responses from paranoid civilizations. Maintaining respectful distances while collecting comprehensive environmental data represents a more subtle approach to intelligence gathering. The spy satellite analogy proves instructive. Military reconnaissance satellites maintain orbits that balance observation capabilities with survivability, often disguising their true purposes behind scientific mission profiles. Weather satellites, communication relays, and navigation systems all provide dual-use capabilities for both civilian applications and military intelligence gathering. Similarly, a probe disguised as a natural comet could collect vast amounts of scientific and strategic data while maintaining perfect operational security. Its spectacular coma and tail would draw attention away from any instrumentation concealed within the nucleus, while its obvious natural appearance would deflect suspicion about artificial origin. But here's where the surveillance hypothesis faces significant constraints from current observations. 3I-ATLAS has displayed no behavior that deviates from natural comet physics. Its carbon dioxide-rich chemistry, while unusual, falls within known ranges of natural variation. Its outgassing patterns correlate precisely with solar heating, rather than following any internal activity cycles that might indicate artificial systems. Most importantly, no non-thermal emissions have been detected. Natural comets produce light through reflected sunlight and fluorescence from excited gas molecules. Artificial systems would likely generate detectable signatures through power generation, data processing, or communication activities. Current spectroscopic observations have found no evidence of such technological emissions. The observational tests for surveillance capabilities become quite specific. Look for narrow-band emissions that don't match known molecular transitions. Search for polarization patterns inconsistent with natural dust scattering. Monitor for temporal variations that correlate with terrestrial radio transmissions or space activity rather than solar forcing. Advanced radar could potentially detect structured objects concealed within the comet's nucleus, though the range limitations and signal attenuation through the coma make such observations extremely challenging. Thermal imaging might reveal temperature distributions inconsistent with purely solar heating, indicating internal heat sources from power generation or data processing systems. The comparison with 1I, Oumuamua, remains relevant here. That object's non-gravitational acceleration without visible outgassing sparked speculation about artificial propulsion systems or light sail-like surfaces. While natural explanations remain under debate, the anomaly demonstrated that interstellar objects can display unexpected behavior that challenges our understanding of natural processes. 3I-ATLAS offers a cleaner test case. Its obvious cometary activity provides a natural explanation for any trajectory modifications through outgassing thrust. Its chemical composition, while unusual, matches known physical processes for volatile sublimation and gas production. Any artificial signatures would have to emerge against this background of normal comet behavior. Risk assessment from a human perspective suggests treating ambiguous objects as scientific opportunities rather than security threats. At current distances and interaction probabilities, 3I-ATLAS poses no conceivable danger to Earth or human civilization regardless of its true nature. Our response should focus on maximizing scientific return through coordinated observations rather than defensive preparations. The surveillance hypothesis ultimately serves a valuable function in sharpening our observational criteria and suggesting specific tests for artificial intelligence, even if those tests confirm natural origin. By thinking like intelligence analysts rather than just astronomers, we develop more sophisticated methods for distinguishing between the signatures of natural processes and artificial systems. Whether 3I-ATLAS represents sophisticated alien surveillance or simply fascinating physics, it's teaching us to see our solar system through external eyes, as an environment that could be characterized, measured, and understood by observers who evolved under distant stars. In that sense, every careful observation we make serves dual purposes: advancing human knowledge while simultaneously demonstrating the level of technological sophistication that hypothetical aliens might expect from our civilization. The watchers, if they exist, are undoubtedly taking notes. The question is whether we're sophisticated enough to recognize that we're being watched, and mature enough to watch them watching us in return. Part 11. The Silent Witness. What if 3I-ATLAS isn't gathering intelligence about us, but instead broadcasting information about its makers? This beacon hypothesis transforms our interstellar visitor from a spy into a lighthouse, a cosmic marker declaring we were here to anyone sophisticated enough to decode the message. The concept of inscribed matter represents one of the most elegant approaches to interstellar communication ever proposed. Instead of broadcasting electromagnetic signals that decay with distance and can be disrupted by stellar interference, advanced civilizations could encode information directly into the atomic and molecular structure of physical objects. Such messages would travel at the speed of matter rather than light, slower, but with perfect fidelity across arbitrary distances and timescales. Consider the advantages of this approach. Radio signals from Earth have been propagating into space for roughly 100 years, but they're already so diluted that they would be undetectable to our own technology at distances of just a few light years. By contrast, physical objects maintain their information content indefinitely if properly preserved. A single comet-sized artifact could carry the equivalent of every book, movie, and digital file ever created by human civilization. The encoding methods could be remarkably sophisticated. Isotope ratios could be artificially manipulated to create detectable patterns that convey mathematical or linguistic information. Crystal lattices might preserve digital data through precise arrangements of dopant atoms that remain stable for millions of years. Complex organic polymers could carry genetic information, cultural knowledge, or technological specifications in sequences analogous to DNA but far more information-dense. 3I-ATLAS presents limited support for the beacon hypothesis based on its trajectory alone. With no close Earth approach, any message it carries would target long-term discoverers rather than immediate recipients. Perhaps the goal isn't communication with any specific civilization, but rather the creation of a galactic information repository, countless artifacts scattered throughout space, waiting for sufficiently advanced civilizations to find and decode them. This approach offers profound advantages over direct contact scenarios. Messages can be precisely crafted without the uncertainties and delays of real-time communication across interstellar distances. Information can be tested, refined, and perfected before launch. Most importantly, the senders retain complete control over what they reveal and to whom, since only civilizations with appropriate technology and motivation would be capable of detecting and decoding the messages. From an archaeological perspective, such beacon objects would represent the ultimate form of cultural preservation. Human civilizations have always struggled with information loss across generations. Libraries burn, languages die, technologies become obsolete. But messages encoded in atomic structure and preserved in the vacuum of interstellar space could maintain perfect fidelity across geological timescales. The detection challenge becomes formidable, however. Current spectroscopic techniques can identify molecular species and measure isotope ratios with impressive precision, but recognizing artificial patterns requires knowing what to look for. Natural processes create their own isotopic signatures through stellar nucleosynthesis, radioactive decay, and chemical fractionation. Distinguishing between natural and artificial patterns demands extremely sophisticated analysis and probably some prior knowledge of the encoding methods employed. Microstructural analysis offers additional possibilities. Crystalline patterns, grain boundary compositions, and microscopic textures might carry information detectable only through direct sampling and laboratory analysis. Such fine-scale encoding would be invisible to remote sensing, but could preserve vast amounts of data in forms that remain stable across cosmic timescales. The philosophical implications extend beyond mere information storage to questions about the purpose and ethics of interstellar messaging. Why would a civilization choose to broadcast information rather than maintaining defensive silence? What knowledge would be worth preserving and transmitting across the galaxy? How should recipients respond to such discoveries? One possibility involves civilizations facing extinction through natural catastrophes, stellar evolution, asteroid impacts, or climate change. Such civilizations might launch technological time capsules as insurance against total obliteration, hoping that their knowledge and cultural achievements would eventually be discovered by other intelligences and preserved for posterity. Another scenario envisions advanced civilizations deliberately seeding the galaxy with educational materials, cosmic textbooks left for younger civilizations to discover when they achieve appropriate technological sophistication. This approach avoids the cultural disruption that direct contact might cause while still enabling knowledge transfer across species and evolutionary lines. Current limitations in our ability to detect such messages shouldn't discourage speculation about their possible existence. Remote sensing provides only crude information about object composition and structure. The kinds of fine-scale patterns that might encode significant information remain largely invisible to telescopic observation, regardless of their actual presence or absence. Future sample return missions from interstellar objects could potentially reveal such encoding through detailed laboratory analysis. Microscopy, mass spectrometry, and crystallographic analysis might detect artificial patterns that remain completely undetectable through remote observation. But such missions lie decades in the future, with current technological capabilities and funding constraints. For now, 3I-ATLAS continues to appear remarkably normal by comet standards, despite its interstellar origin and unusual chemistry. Its carbon dioxide-rich composition might simply reflect natural formation processes in a cold stellar environment rather than any form of artificial encoding. Its morphological evolution follows predictable patterns based on solar heating and volatile sublimation without obvious anomalies that would suggest artificial control or information content. Yet the absence of obvious beacon signatures doesn't eliminate the possibility entirely. The most sophisticated messages might be designed to remain undetectable until recipients possess appropriate decoding technologies and theoretical frameworks. We might be looking at a cosmic library without recognizing the books on its shelves. Even if 3I-ATLAS proves entirely natural, it still serves as a beacon of sorts, a messenger carrying information about chemical processes in distant stellar systems, the dynamics of interstellar matter transport, and the diversity of conditions that characterize planetary formation throughout the galaxy. Every spectroscopic measurement adds to our understanding of cosmic evolution and the processes that shape matter across space and time. The universe speaks to us constantly through such natural messengers. The question driving our investigation is whether some of those messages might be more than merely chemical, whether they might carry the deliberate thoughts and intentions of minds that once contemplated the same mysteries we ponder today. Whether natural or artificial, 3I-ATLAS reminds us that we live in a galaxy where information travels not just as electromagnetic radiation but as matter itself, cosmic bottles carrying messages across the vast ocean of space, waiting for patient beachcombers to discover what stories they might tell. Part 12. The Universe as a Laboratory. Earth occupies a unique position in our cosmic neighborhood, the only confirmed biosphere within dozens of light years, a living laboratory where chemistry has organized itself into self-replicating systems of staggering complexity. From an external perspective, our planet might represent the ultimate scientific opportunity, a controlled experiment in biological evolution observed from a respectful distance. This laboratory hypothesis asks whether 3I-ATLAS might represent part of a long-term observational study of terrestrial life. Not intervention or interference, but careful scientific monitoring of evolutionary processes that unfold across geological timescales. The question transforms our visitor from reconnaissance probe or cultural beacon into something far more subtle, a scientific instrument designed to understand how life develops on planets like ours. Modern science already treats Earth as a case study in habitability through the emerging field of astrobiology. We analyze our planet's atmospheric composition, surface chemistry, and biological signatures as proxies for what we might expect to find on exoplanets orbiting distant stars. The techniques we use to study our own biosphere, spectroscopic analysis of atmospheric gases, monitoring of seasonal vegetation cycles, characterization of biogeochemical processes, could easily be applied by external observers studying us. But here's where the hypothesis immediately encounters significant constraints from observable facts. 3I-ATLAS will pass no closer to Earth than 1.6 astronomical units, roughly 250 million kilometers. This distance makes detailed study of terrestrial biological processes essentially impossible with any conceivable technology. Earth would appear as nothing more than a pale blue dot, its biosignatures detectable only through the most sensitive atmospheric spectroscopy. For comparison, our most sophisticated space telescopes can barely detect the atmospheric compositions of Jupiter-sized exoplanets orbiting nearby stars. Characterizing the complex atmospheric chemistry that indicates biological activity on Earth-sized worlds remains at the cutting edge of our technological capabilities, even with instruments specifically designed for such observations. If advanced civilizations wanted to study Earth's biosphere in detail, they would need to position monitoring systems much closer to our planet. Lagrange point locations, co-orbital positions with Earth, or high-inclination solar orbits would provide far better observation platforms than hyperbolic interstellar trajectories that spend only months in our inner solar system. This constraint suggests that any experimental monitoring represented by 3I-ATLAS would focus on broader heliospheric conditions rather than detailed biological processes. The probe's trajectory samples solar wind characteristics, magnetic field variations, and cosmic ray environments that affect planetary atmospheres throughout our solar system. Such data could reveal general habitability conditions without requiring close approaches to individual worlds. The philosophical backdrop involves competing theories about the rarity of complex life in the universe. The rare Earth hypothesis, proposed by Peter Ward and Donald Brownlee, suggests that while simple microbial life might be common throughout the galaxy, complex multicellular organisms requiring specific planetary and stellar conditions might be extraordinarily rare. Earth's biosphere could represent a precious scientific specimen worthy of careful long-term study. Conversely, the principle of mediocrity suggests that Earth's conditions and biological evolution might be relatively common among rocky planets in habitable zones around sun-like stars. If life is abundant throughout the galaxy, then individual biospheres might be less scientifically valuable and less likely to justify dedicated monitoring missions. Recent discoveries of potentially habitable exoplanets, Kepler 452b, TRAPPIST-1 system worlds, Proxima Centauri b, suggest that Earth-like planets might indeed be common in our galactic neighborhood. This abundance would reduce the scientific motivation for intensive study of any individual biosphere, since similar experiments would be occurring on countless worlds throughout the galaxy. The anthropic principle adds another layer of complexity to these considerations. Observers inevitably find themselves in environments compatible with observation. We exist in conditions that permit our existence, which tells us nothing about whether such conditions are common or rare in the broader universe. This selection effect makes it difficult to assess whether Earth represents a typical outcome of planetary evolution or an extraordinary exception worthy of special attention. If the laboratory hypothesis has any utility, it lies not in explaining 3I-ATLAS specifically, but in pushing us to think about what kinds of observations would actually surprise us. What signatures would indicate systematic study rather than natural processes? What patterns would suggest experimental manipulation rather than evolutionary happenstance? Genuine experimental interventions might leave detectable traces. Periodic introduction of organic compounds with unusual isotopic signatures could potentially be tracked through geological records. Systematic modification of atmospheric chemistry might show up in ice core data or sedimentary deposits. Even subtle genetic modifications in terrestrial organisms might be detectable through comparative genomics, though distinguishing such interventions from natural evolutionary processes would be extraordinarily difficult. More plausibly, long-term observational studies might focus on characterizing heliospheric conditions that affect planetary atmospheres and climate systems. Solar wind variations, cosmic ray flux changes, and magnetic field fluctuations all influence atmospheric chemistry and biological evolution in ways that external observers might want to understand for comparative planetology studies. The ethical dimensions of such research become fascinating to contemplate. How would advanced civilizations balance scientific curiosity with non-interference principles? What guidelines might govern the study of primitive civilizations? How would they weigh the scientific value of detailed observations against the risks of cultural contamination or psychological trauma from revealed surveillance? Our own scientific ethics provide some guidance here. Modern anthropology and ecology operate under strict protocols designed to minimize impact on study subjects while maximizing scientific understanding. Observational studies are preferred over interventional experiments when studying complex systems that might be disrupted by direct interference. Similar principles might govern interstellar research programs conducted by civilizations millions of years more advanced than our own. The recognition and respect considerations raise profound questions about appropriate responses to confirmed surveillance. Should humanity attempt to communicate with hypothetical observers? Should we modify our behavior knowing we might be watched? Should we deliberately signal our awareness of potential monitoring to demonstrate our growing scientific sophistication? For now, these remain entirely speculative questions, since 3I-ATLAS continues to display behavior consistent with natural comet physics. Its carbon dioxide-rich chemistry reflects formation conditions in its parent stellar system rather than any obvious experimental purpose. Its trajectory samples heliospheric conditions without approaching Earth closely enough for detailed biosphere monitoring. Yet the laboratory hypothesis serves a valuable function in expanding our thinking about potential motivations for interstellar visitation. Not all alien contact scenarios involve conquest, trade, or direct communication. Some might involve patient scientific study conducted across geological timescales by civilizations whose research programs span millions of years. The universe already conducts vast experiments in biological evolution on countless worlds throughout the galaxy. The question driving our investigation is whether some of those experiments might be observed, recorded, and analyzed by conscious minds seeking to understand the deeper patterns that govern life's emergence and development across cosmic scales. Whether 3I-ATLAS represents such scientific observation or simply natural cosmic debris, it reminds us that Earth exists within a larger context of galactic evolution and astronomical processes. We are not isolated observers studying the universe from outside. we are part of the experiment itself, temporary arrangements of matter and energy that have achieved the remarkable property of self-awareness and scientific curiosity. In that sense, every observation we make of 3I-ATLAS simultaneously advances human knowledge and demonstrates the level of scientific sophistication that Earth-based intelligence has achieved. We are studying the universe while the universe, through us, studies itself. The laboratory experiment continues, and we have become both subjects and scientists in the grand investigation of cosmic evolution. Part 13. Other Suspects in the Sky. To understand the significance of 3I-ATLAS, we must place it within the growing catalogue of interstellar visitors that have graced our solar system in recent years. Each object tells a different story, revealing the diversity of materials and processes that characterize planetary systems throughout our galactic neighborhood. 1I, Oumuamua, remains the most enigmatic member of this collection. Discovered on October 19, 2017, this cigar-shaped object displayed non-gravitational acceleration without any visible signs of outgassing, behavior that challenged every model of natural comet and asteroid physics. The Spitzer Space Telescope's infrared observations detected no thermal emissions from sublimating volatiles, yet something was pushing Oumuamua faster than gravity alone could account for. The controversy spawned multiple competing explanations, each with significant strengths and weaknesses. Marco Micheli's team, publishing in Nature, documented the acceleration precisely but couldn't identify its source. The hydrogen iceberg model proposed invisible H2 sublimation, but molecular hydrogen ice shouldn't survive millions of years in the interstellar radiation environment. The nitrogen iceberg hypothesis suggested fragments of Pluto-like crusts, but required implausibly large parent bodies to produce kilometer-sized chunks. Abraham Loeb and Shmuel Bialy's radiation pressure hypothesis offered an elegant alternative. If Oumuamua possessed an extremely low density and high surface area, essentially a thin sheet, then solar radiation pressure alone could explain the observed acceleration. This light sail-like explanation proved both testable and controversial, sparking debates that continue today about the boundary between natural phenomena and artificial artifacts. 2Y. Borisov presented a stark contrast when discovered by amateur astronomer Gennady Borisov on August 30, 2019. This object behaved like a textbook comet, displaying vigorous outgassing, a substantial coma, and clear tail development as it approached perihelion. ALMA radio telescope observations revealed unusually high carbon monoxide concentrations, among the highest ever measured in any comet, suggesting formation in extremely cold regions of its parent stellar system. Hubble Space Telescope, monitoring through 2020, documented minor fragmentation events, with small pieces breaking away from the main nucleus in a process entirely consistent with natural thermal stress and structural weakness. These observations provided our first detailed look at how interstellar comets behave under solar heating, establishing baseline expectations for natural versus artificial activity. Now, 3I-ATLAS adds a third data point to this emerging picture. Its carbon dioxide-dominated chemistry differs markedly from both Oumuamua's apparent lack of volatiles and Borisov's carbon monoxide richness. This chemical diversity suggests that interstellar objects sample a wide range of formation environments and stellar system conditions throughout the galaxy. But the story doesn't end with these three confirmed interstellar objects. In 2022, the U.S. Space Command issued a memo asserting 95% confidence that a meteor detected by Department of Defense sensors on January 8, 2014, had originated from outside our solar system. This interstellar meteor, designated I-MON, reportedly entered Earth's atmosphere at approximately 60 kilometers per second and exploded over the Pacific Ocean near Papua New Guinea. The claim sparked intense scientific debate. Harvard's R.V. Loeb organized expeditions to recover fragments from the ocean floor, reporting the discovery of metallic spherules with unusual compositions that might represent the first recovered samples of interstellar matter. However, These claims remain contested within the scientific community, with critics arguing that the initial velocity measurements were insufficient to prove interstellar origin and that the recovered spherules could represent terrestrial contamination or normal meteoritic materials. Additional interstellar meteor candidates have been proposed, including IM2 detected in 2017, but these objects present even greater observational challenges. Unlike the large, long-lived objects that astronomical surveys can track for months, interstellar meteors provide only seconds of observational data before disintegrating in Earth's atmosphere. The pattern that emerges from these diverse objects challenges any simple explanation involving artificial origin. If extraterrestrial civilizations were sending probes to our solar system, we might expect some consistency in design philosophy, chemical composition, or behavioral characteristics. Instead, we observe remarkable variety that more naturally explains as debris from multiple stellar systems with different formation conditions. Oumuamua's acceleration anomaly remains genuinely puzzling, but it represents an outlier rather than part of a consistent pattern. Borisov's high carbon monoxide content reflects natural chemistry in cold protoplanetary environments. 3I-ATLAS's carbon dioxide richness suggests yet another formation environment, possibly closer to the CO2's ice line in its parent system. This diversity actually strengthens the case for natural origins, while providing fascinating insights into planetary formation processes throughout the galaxy. We're seeing direct samples of materials that condensed in stellar systems with different temperature gradients, chemical compositions, and evolutionary histories. Each object serves as a cosmic core sample, revealing conditions that existed billions of years ago in distant regions of space. The upcoming Vera Rubin Observatory will revolutionize our understanding of these phenomena by dramatically increasing detection rates of interstellar objects. Current surveys discover perhaps one interstellar visitor per year, but Rubin's wide-field capabilities could reveal dozens annually. This statistical improvement will help distinguish between natural diversity and potentially artificial patterns while advancing our understanding of galactic ecology and matter transport between stellar systems. For technosignature research, the diversity of interstellar objects provides both challenges and opportunities. The challenge lies in recognizing artificial signatures against a background of natural chemical and morphological variation. The opportunity comes from developing increasingly sophisticated analysis methods that can distinguish between natural and artificial processes with high confidence levels. 3I-ATLAS benefits from this growing comparative context. We now know that interstellar objects can display unusual chemistry, Borisov's CO richness, unexpected behavior, Oumuamua's acceleration, and diverse compositions that reflect their formation environments. Against this background, 3I-ATLAS appears relatively normal, a comet with somewhat unusual but not unprecedented chemistry, following predictable behavior patterns as solar heating drives volatile sublimation. Yet each new discovery expands our understanding of what's possible in the realm of interstellar debris. The universe continues to surprise us with objects that challenge our models and assumptions about natural processes. Whether any of these surprises ultimately prove to involve artificial rather than natural phenomena remains an open question, one that requires careful observation, rigorous analysis, and the intellectual humility to distinguish between what we hope to find and what nature actually reveals. The sky above us carries messages from throughout the galaxy, chemical signatures of distant worlds, physical remnants of ancient stellar processes, and perhaps, just perhaps, the technological artifacts of civilizations that achieved spaceflight long before Earth had even formed. Our task as scientists is to read these messages carefully, separate signal from noise, and remain open to discoveries that might challenge our deepest assumptions about life and intelligence in the universe. Part 14. The supernatural layer. Throughout human history, comets have served as cosmic punctuation marks in the story of civilization, harbingers of change, omens of doom. and celestial messengers that demanded interpretation by those who witnessed their ethereal displays. This cultural layer of meaning-making preceded scientific understanding by millennia, and its psychological residue continues to influence how we react to unusual objects in the sky. Julius Caesar's assassination in 44 BCE coincided with the appearance of a brilliant comet that Romans interpreted as the dictator's soul ascending to join the gods. This, Julian star, became a powerful political symbol, appropriated by Caesar's heir Octavian to legitimize his claim to power. The comet appeared in artwork, coins, and architectural decorations throughout the Roman Empire, transforming a natural astronomical event into a cornerstone of imperial propaganda. Ancient civilizations maintained surprisingly sophisticated records of cometary appearances. Babylonian astronomers tracked Halley's comet for over 2,000 years, documenting its periodic returns with enough precision to retrospectively identify historical appearances that weren't recognized as the same object until modern orbital calculations revealed their common identity. Chinese court astronomers recorded comets as indicators of dynastic stability, interpreting their brightness, duration, and tail characteristics as signals about imperial legitimacy and cosmic approval. Medieval European chronicles overflow with accounts of comets coinciding with battles, plagues, political upheavals, and natural disasters. The Great Comet of 1066, now known to be Halley's Comet, appeared just months before the Norman conquest of England, and was later depicted in the Bayeux Tapestry as a portent of Harold Godwinson's defeat at the Battle of Hastings. The scientific revolution gradually replaced supernatural interpretation with physical understanding. Edmund Halley's calculation of cometary orbits demonstrated that these objects followed predictable gravitational mechanics rather than divine whim. Spectroscopic analysis revealed their chemical composition: water, carbon dioxide, carbon monoxide, and other volatile compounds sublimating under solar heating. Space missions to comets like Giotto's encounter with Halley in 1986 provided direct measurements of their nucleus composition and internal structure. Yet the emotional resonance persists. Spectacular comets like Hale-Bopp in 1997 and Neowise in 2020 generated worldwide public fascination that transcended purely scientific interest. Social media amplifies this effect, with dramatic comet photography spreading rapidly through networks that celebrate natural beauty alongside conspiracy theories and supernatural interpretations. Modern myth-making faces similar psychological temptations to those that affected ancient observers. Anomalous observations get amplified through selective reporting and confirmation bias. Anti-tail formations, fragmentation events, and unusual chemical compositions trigger speculation about artificial intervention or extraterrestrial visitation. The boundary between legitimate scientific hypothesis and wishful thinking becomes blurred when dealing with phenomena that challenge our existing understanding. 3I-ATLAS sits at this fascinating intersection of ancient wonder and modern precision. Its interstellar origin makes it literally a messenger from another star system, a poetic reality that rivals any mythological interpretation. The carbon dioxide-rich chemistry detected by James Webb Space Telescope provides factual information about conditions in distant stellar environments that our ancestors could never have imagined accessing. But we must carefully separate optical illusions from physics, normal behavior from genuinely anomalous signatures. The same pattern recognition that helped our ancestors survive by detecting meaningful signals in noisy environments can generate false positives when applied to astronomical phenomena. Faces in clouds, intention in randomness, design in natural processes, these cognitive biases required constant vigilance in scientific investigation. Advanced image processing and statistical analysis help mitigate these psychological factors. Machine learning algorithms can identify subtle patterns in spectroscopic data while avoiding the pareidolia that affects human visual interpretation. Automated survey systems detect and catalog thousands of objects without the emotional investment that might bias human observers towards seeing what they hope to find rather than what actually exists. the responsibility becomes particularly acute when communicating scientific results to public audiences. Headlines that sensationalize anti-tail formations or unusual chemistry can propagate misunderstanding faster than corrections can follow. The balance between conveying genuine scientific excitement and avoiding misleading speculation requires constant attention to language, context, and evidence standards. 3I-ATLAS represents a genuine marvel regardless of its ultimate explanation. This object, formed in another stellar system billions of years ago, survived the journey through interstellar space and arrived in our solar system at precisely the moment when human technology achieved sufficient sophistication to study it in detail. The James Webb Space Telescope observations provide our first high-resolution spectroscopic analysis of an interstellar visitor before it reaches perihelion, a scientific opportunity that would have been impossible just a few years earlier. The timing seems almost supernatural in its convenience, but it reflects the intersection of natural astronomical processes with human technological development rather than any divine intervention or alien scheduling. Survey telescopes like ATLAS discover interstellar objects when they exist and when our detection capabilities reach appropriate sensitivity levels. Advanced spectroscopic instruments like JWST reveal chemical compositions when their observational windows align with funding decisions made years earlier. This narrative of coincidence and discovery contains its own form of magic, the magic of scientific method revealing hidden patterns in natural phenomena. Whether 3I-ATLAS proves to be entirely natural or contains unexpected artificial signatures, it represents a triumph of human curiosity and technological capability. We can now analyze the chemical composition of objects that originated in stellar systems dozens of light-years away, detecting molecular species and isotope ratios with precision that would have seemed miraculous to ancient astronomers. The universe provides enough genuine wonder to inspire awe without requiring supernatural explanation or alien intervention. Stellar nucleosynthesis creates the elements that compose our bodies across billions of years of cosmic evolution. Gravitational dynamics scatter debris between star systems on trajectories that occasionally bring distant worlds within reach of our telescopes. Chemistry and physics operate according to principles elegant enough to predict cometary behavior, while revealing the fundamental unity underlying apparent diversity. Sometimes the most profound magic lies not in discovering that wizards exist, but in understanding how nature performs tricks sophisticated enough to inspire centuries of supernatural interpretation. 3I-ATLAS continues this tradition, a cosmic illusion that challenges our assumptions while rewarding careful observation with insights into processes that shaped matter throughout the galaxy long before Earth had even formed. The ancient observers were right about one thing: comets do carry messages from the heavens. They were wrong only about the nature of those messages, which proved to be far more wonderful than mythology imagined: chemical signatures of stellar evolution, gravitational dynamics of planetary formation, and physical processes that connect our local environment to the broader cosmos in ways that dwarf any human conception of divine intervention. Part 15. The Final Ambiguity. We return now to the central question that has guided this investigation. If 3I-ATLAS were designed, by whom, for what purpose, and why now? After examining evidence from multiple perspectives, surveillance, communication, seeding, reconnaissance, archaeology, we find ourselves confronting not answers, but a deeper appreciation of the ambiguities that make this question so compelling. Let's summarize what we've learned through careful observation. 3I-ATLAS follows a hyperbolic trajectory with an eccentricity of approximately 6.08 and a velocity at infinity of 57 to 61 kilometers per second, clearly marking its interstellar origin. It approaches no closer to Earth than 1.6 to 1.8 astronomical units, ruling out direct interaction scenarios. James Webb Space Telescope spectroscopy reveals carbon dioxide-dominated chemistry with unusual CO2 to water ratios that hint at formation near a CO2 ice line in its parent stellar system. Hubble observations show typical comet morphology with coma development and dust tail formation consistent with natural volatile sublimation under solar heating. The size remains constrained to an upper limit of approximately 5.6 kilometers, though the nucleus could be significantly smaller. No fragmentation has been confirmed as of current observations, though thermal stress near perihelion could trigger breakup events common among natural comets. The trajectory planning, if artificial, seems suboptimal for Earth-specific reconnaissance, but adequate for heliospheric sampling or general solar system characterization. This presents us with two primary interpretations, each internally consistent but requiring different evidential standards. Interpretation A suggests natural origin. 3I-ATLAS represents a comet ejected from a stellar system with unusual chemistry, perhaps formation closer to the CO2 ice line than typical in our solar system. Its behavior under solar heating follows predictable patterns based on volatile sublimation and dust liberation. Chemical diversity among interstellar objects reflects the range of formation environments throughout the galaxy. Interpretation B proposes artificial origin. 3I-ATLAS represents a camouflaged probe exploiting natural comet physics to disguise sophisticated instrumentation. Its chemical composition provides thermal buffering and radiation shielding for internal systems. Outgassing creates natural concealment for any artificial emissions or propulsive effects. The trajectory samples heliospheric conditions valuable for understanding our solar system's characteristics. Current evidence supports interpretation A more strongly, but interpretation B remains unfalsified by available data. The critical observations that could distinguish between these possibilities lie ahead during the perihelion passage around October 30th, 2025, and subsequent monitoring through December 2025 when 3I-ATLAS re-emerges from solar glare. What discoveries would definitively change our assessment? Repeatable non-solar modulations in dust or gas production would indicate internal activity cycles inconsistent with natural heating patterns. Detection of refined metals, artificial compounds, or unusual crystalline structures would suggest manufacturing processes rather than natural condensation. Anomalous line emissions at wavelengths that don't match known molecular transitions could reveal technological systems. Most compelling would be encoded signals, patterns in outgassing timing, dust grain compositions, or electromagnetic emissions that convey information rather than merely reflecting physical processes. Abraham Loeb's contributions to this field deserve recognition regardless of whether his specific hypotheses prove correct. The radiation pressure explanation for Oumuamua's acceleration, while controversial, generated testable predictions and stimulated more sophisticated analysis of interstellar objects. His broader framework for technosignature research, distinguishing artificial from natural phenomena through rigorous observational criteria, advances the field even when applied to objects that ultimately prove natural. The scientific ethos requires maintaining extraordinary evidence standards while remaining open to discoveries that challenge existing paradigms. We must resist both the uncritical acceptance of exotic explanations and the reflexive dismissal of possibilities that seem unlikely based on current understanding. The universe has repeatedly surprised us with phenomena that exceeded our theoretical expectations, from quantum mechanics to dark energy to extremophile organisms thriving in environments once considered uninhabitable. Our responsibility to public communication becomes particularly crucial given the potential for misinformation around topics involving possible extraterrestrial intelligence. Clearly labeling speculation as such, updating assessments as new peer-reviewed results become available, and maintaining separation between evidence and inference help prevent the propagation of unfounded claims that could undermine legitimate scientific inquiry. The James Webb Space Telescope observations published in preprint form represent preliminary results that require peer review and confirmation before reaching definitive conclusions. As solar heating intensifies during 3I-ATLAS's approach to perihelion, increasingly sophisticated spectroscopic analysis could reveal molecular signatures that either support natural formation scenarios or suggest something more complex. The metaphor of a locked door in space captures the essence of our current situation. We can observe the door's exterior features, its size, composition, trajectory, and surface properties, but we cannot yet determine whether it opens onto natural processes or artificial intelligence. Sometimes the most profound discoveries emerge not from finding the key that unlocks such doors, but from learning to ask better questions about what we might find behind them. The search for technosignatures in objects like 3I-ATLAS serves valuable scientific purposes regardless of the ultimate answers. It pushes us to develop more sophisticated analysis techniques, consider alternative explanations for anomalous observations, and maintain rigorous evidential standards in the face of extraordinary claims. Even confirming natural origins advances our understanding of interstellar debris, planetary formation processes, and the chemical diversity that characterizes stellar systems throughout the galaxy. As we approach the critical observational period of late 2025, multiple ground-based and space-based telescopes will monitor 3I-ATLAS with unprecedented precision. The James Webb Space Telescope, Keck Observatory, Very Large Telescope, and Hubble Space Telescope will track its evolution as solar heating drives increasingly vigorous activity. These coordinated observations represent our best opportunity to distinguish between natural and artificial explanations for this enigmatic visitor. The outcome will advance human knowledge regardless of which interpretation proves correct. If 3I-ATLAS is natural, we gain insights into chemical processes in distant stellar systems and the mechanisms that transport matter between stars. If it contains artificial elements, we face the profound challenge of recognizing and responding to evidence of extraterrestrial intelligence. In either case, the investigation exemplifies the scientific method at its most sophisticated, careful observation, rigorous analysis, and intellectual humility in the face of cosmic mysteries that dwarf human experience. We remain patient observers, watching the evidence wherever it leads, prepared for discoveries that might transform our understanding of life and intelligence in the universe. The silence between the stars may yet hold voices we have not learned to hear. But first, we must perfect our ability to distinguish between the whispers of physics and the possibility of something more, something that chose to visit our solar system disguised as a dirty snowball from the stars, carrying secrets we are only beginning to know how to read. The locked door drifts past us at 61 kilometers per second. Whether it opens onto natural wonders or artificial marvels, the universe continues to teach us patience, precision, and the profound humility that comes from recognizing how much we have yet to learn about the cosmos we inhabit.